Alright guys, welcome back. So in the last video I went ahead and covered how to break down negative radicals, and we used our imaginary number I in order to get those answers. We're going to take this a step further, and a lot of this is going to be kind of a review, but we're going to cover it anyway. And then I want to introduce something brand new called conjugates. Alright, so let's start with step 1. Complex numbers work a lot like a regular number with a variable in it. So something like 8i 8i can be treated much the same as something like 8x. Okay? In fact, whenever you have operations with complex numbers, so if we're adding, subtracting, multiplying, dividing, whatever else, you can pretty much treat it like an x until the very, very end of the problem. Then you have to switch it all back to I. Alright? I'm going to go ahead and show that process with the simpler things, but at the more complex things, I'm going to go ahead and ignore it. But just remember, you can always replace all of your i's with x's until the very, very end of your problem where you can't go any further, and then you switch them all back to i's. Alright, so let's just start with adding complex numbers. Really, really simply, okay? So this is going to be adding. This should have been neater, and I should have left myself a space for this, but adding complex numbers. Alright, 8i plus 3i. Remember, treat it like an x, and I'm going to go ahead and rewrite this as 8x plus 3x. So if we were doing 8x plus 3x, I think most everyone would be willing to agree that 8 plus 3 is 11, and remember, these are like terms, so remember your like terms rules. They both have the same letter, and that letter has the same degree or same exponent, so we can go ahead and add them together. And from here on, remember at the end of your steps, if I was adding 8i plus 3i, I told you just remember to replace your x. In this case, 11i. Okay? So like I said, adding complex numbers, this goes the same for subtracting. So if I do a subtracting section over here, and I'm just going to shorten that to but that stands for subtracting, okay? So let's pretend it's just 8i minus 3i. Again, a lot of you guys won't have issues with this, so that'd be like 8i minus 3i. And 8i minus 3i would just give us that, I'm sorry. Oop. Well, the example was x, sorry, so there. Remember, you can replace it with an x is what I meant to do. I just kind of made that sloppy. But 8x minus 3x would give you that 5x. And remember at the end, just switch out your x with your I. This shouldn't be difficult for those of you that know how to combine like terms. This is all the same thing. We're going to do the same thing with multiplication, and this is where it gets a little more complex. So with multiplication and and division, it does take a step in a different direction. So I'll still use green to represent my x's, but and I'll do one example of this. So here's multiplication. I'm going to shorten it to mult. Okay, so mult is multiplication. And we're going to use those same numbers, 8i. This time, instead of plus, instead of minus, we're going to do times 3i. And you can represent this with a dot. I'm going to represent it with a parentheses just because I feel like doing it this way. Alright, 8i times 3i. And again, what you can redo is you can treat it as x's. I don't personally like replacing them with x's. I actually think it makes the problem a lot more complex. But it's just to show you already know what to do with this, even if it hasn't been taught to you. So 8x times 3x just gives us 8 times 3 gives you that 24, and that x times x gives you that x squared. Alright, remember your last step is we're just going to switch the problem back, and we're going to write it as 24, replace your x with an I. That squared still remains. Alright. The last step, here's what's different about complex numbers as opposed to x. This is like the major difference here, is that when I have I to some power, it can be a different value. So your goal in any I problem is to get it down to just I to the first power. If you can get it down to I to the first power, you are all good. Okay? So let me go ahead and grab our chart from last time. In our last video, I went ahead and wrote this down. For those of you that don't have this memorized yet, it's not a big deal. Your big one is this I to the second power. If you can memorize I to the second power, you will be golden. Okay, I to the second power is -1. You should memorize all four. It'll make your life a lot easier. You'll be able to handle every type of problem, but as long as you know your I squared equals -1, you can handle most problems. Okay, so there's your chart. I squared equals -1 for those that don't remember. So instead of writing 24i squared, I can write this as 24 times, and remember it's no longer I squared, it's actually a -1. You just saw on the chart that it equals -1. And what is 24 times a negative 1? It's just that negative 24. And this is how complex numbers differ from x. This is like the main part of why we have complex numbers and what we do with them as far as math problems go. All right? So I'm going to go ahead and move on. Let me get all of these on one page real quick. So that's that whole page of notes. All right? Addition, subtraction, multiplication. And there shouldn't be any difficulty with this thus far. So now I'm going to go ahead and do an example of division, and this is going to take a different step. We're going to introduce something called the conjugate here, okay? So one rule that you have to have is you cannot have I probably should have written that in a different color, in the denominator. Remember, the denominator is the bottom of your fraction, okay? In all of these previous examples, so you cannot have I in the denominator. All of these previous examples, sorry, that's the wrong page. Give us a bunch of answers that have 11i. This is like 11i over 1, 5i over 1, negative 24 over 1. None of these have an I in the denominator because they don't really have one. However, what if I gave you a problem like this? 3i over 9i squared. Okay? 3i over 9i squared. Clearly an I in the denominator, and there are a million and one ways to simplify this. Alright? I'm going to simplify it one way that forces us to do a little bit of mathematics here, because I don't want... Actually, this is a really bad example to start off with. That'll just show you guys too many complications. So we'll go ahead and just go with like 3 over 9i. Alright, real simple example. The first thing I'll always recommend is with any fraction in any kind of math problem is to go ahead and reduce it. One thing that you'll notice here is that I purposely went ahead and gave us 3 over 9. 3 over 9 simplifies. Alright, so 3 goes into 3, 1 time, 3 goes into 9, 3 times. So what you've really got here is a 1 over 3 times I. Alright, and now this is our simplified version. And this is where I would consider really square one. Your job, because you cannot have I in the denominator, the way we get rid of it is much like you did in that multiplication problem. So keep in mind on that last page, what you guys did was you had down here, that 8x times 3x gave you that x squared, or that I squared. I squared simplified to negative 1 because we have a value for that. Remember your table, okay? Your table is that I squared equals negative 1, but there are a bunch of other values on there. The goal is to get your I to some even numbered power. If you get it to an even numbered power, you'll be able to reduce it to either negative 1 or positive 1, depending on which one. So I to the second would be negative 1, I to the fourth is positive 1, I to the sixth is negative 1, I to the eighth is positive 1, and it'll just keep cycling over and over and over like that. So if we can get ours to an even powered exponent, we will be in good shape. Alright? So what is the closest even powered exponent to I to the first? You'll notice that I to the first is I to the 1, so the closest even powered exponent would be to get it to I to the second. Okay? Technically you could do this problem with I to the fourth, or I to the sixth, or any even numbered exponent, but it is easiest to get it to the one that is closest. Alright, so closest thing to I to the first is I to the second. I'm going to go ahead and ask you now, what would I multiply times I? I times what gives you I to the second? Keep in mind, this is like asking x times what equals x to the second. X times x equals x to the second, so I times I must equal I to the second. And what you're going to do is you're going to multiply by I over I. To explain why it has to be I over I, think back to fractions in an example like this. 1/2 plus 2/3. You had to get a least common denominator here, which most people will notice that 2 and 3 both go into 6. But to do that, it's not like you multiplied by 1 over 3 just to change this over to a 6. That's not the same value, so you had to do 3 here. Over here, you had to do 2 over 2. And you were taught this in like grade school and whatnot. So it's as simple as getting a similar denominator. So here, 3 times 1 would be 3, 3 times 2 is 6, plus 2 times 2 is 4, 3 times 2 is 6, gives you at the end 7 over 6. Now, this problem doesn't really matter, but the purpose was to understand that you have to multiply by something over itself in order to not change the problem. because 1/2 and 3/6, if you type in 1 divided by 2, you get 0.5. If you type in 3 divided by 6, you get 0.5. If you type in 2 divided by 3, you get 0.666 repeating. If you type in 4 divided by 6, you get 0.666 repeating. So you'll notice that it's the same problem, I just changed the way it looked. The numbers, the actual value of the numbers is the same. Same thing has to happen here. If I don't multiply by I over I, if I multiply this by like 1 over I, you'll get a different value. 1 over I is not the same as I over I. Alright? You have to have some version of 1, some number over itself. In this case, we're using I. Alright? So if we ignore all this and get back to our main problem, we're just going to multiply across. 1 times I is just that 1I over 3i times I gives you what we were looking for. I told you the goal was to get it to an even powered exponent. There it is. First things first, you don't really typically write this as 1 times I. 1 times I is just I. Alright? And then remember your I squared simplifies. So this is like 3 times I squared is what value? So you should start to remember I squared is equal to -1. Alright? And 3 times -1 just equals that -3. So your final answer here is that I over -3. Also, I don't really care if you write this as -I over 3 or -I over 3 like this. All three of these answers are acceptable. I really don't care if the negative sign is dead even, on the bottom, on the top. It doesn't really matter to me at all. And most mathematicians really don't care, I don't think. Technically, this is a standard. Alright. So you cannot have I in the denominator, so your goal is to get an even powered exponent on your I. In this case, we wanted to get 3i to the first to 3i to the second. The easiest way to do that is to multiply by I. Alright. We're going to introduce one more thing in this video, and that's going to be your conjugate. So I'm going to go ahead and move pages now. Again, I'm going to show you all these pages at the very end of this video, so if you need to, go ahead and skip to the end and copy that, or skip back. It's up to you. So let's go ahead and introduce the conjugate. Conjugate. Conjugates are going to be used primarily with imaginary numbers where we have binomials with I in the denominator. An example like this. Well, actually, let's go ahead and define what a conjugate is. Or, if you want to find out what the definition of a conjugate is, feel free to go on Wikipedia, but it's really fancy. For your purposes, if you're watching this video, again, you're not comfortable with this material, I wouldn't bother learning the wiki definition. It's fancy and whatnot, but the point of a conjugate is that you're going to eliminate the outer and inner terms of FOIL. Your conjugate's just going to make your life easier. So we're going to use this to simplify binomials with I. Alright? This will not help some of you. Some of you guys might have math teachers that really want you to memorize the definition of a conjugate. As a teacher, personally, I don't care if you can define anything in mathematics. I really don't care for wordy, verbose definitions of math words. I just don't see the point. So I'm just going to teach you how to use the conjugate rather than define it. Alright? So your conjugate is real simple, and here's how we'll define it. We'll actually define it just by showing you a couple of examples. Alright, so if I have, example, if I have something like 3 plus 2i, your conjugate, which I will always write in blue for this page, so your conjugate, which I'll simplify to conj, is 3 minus 2i. All you're doing is simplifying this operation in the middle here. Okay? Again, let's go ahead and get another example like 1. Oh, that's a 1. 1. It's a really sloppy 1, but pretend that is a proper 1. 1 plus 120i. The conjugate is just going to be 1 minus 120i. And you would continue with this pattern, so 10 plus 2i would be 10 minus 2i, 90 plus I is now 90 minus I, but it's always going to be this middle operation that you're changing. Conversely, the conjugate of this, so the conjugate of 3 minus 2i, is 3 plus 2i. So they go back and forth. They're called a conjugate pair. Okay? And what you're going to do with your conjugate pairs is you're going to use them for all of these binomials with I. Let's go ahead and give an example of that. I don't know. Let's go ahead and Here's some examples that we would simplify. 3 over 2 minus 2i. Alright, and the reason that I use these particular numbers is because I'm avoiding doing anything that would be overly complex, so I don't want you to have to simplify, but your first step technically would be to look at this problem and be like, well, is there any number that can go into 3, 2, and 2? In this case, there's not. I gave you guys one that doesn't reduce, but start with that reduction step, okay, and make sure that there isn't anything that happens to match up. And then what you're going to do is you're going to multiply this by the conjugate of your denominator. Okay? Fancy way to say it, but remember you already know your conjugate, you're just changing the sign, right? So you're going to multiply it by whatever this conjugate is over itself. What's the conjugate of 2 minus 2i? Remember? So minus minus, you're just going to switch it to a plus. This is going to be 2 plus 2i. And I told you guys earlier that we always multiply by some version of 1, so it over itself. For purposes of this is a little different. As a teacher, I don't really require people to go all the way with this, just because in factoring, simplifying all the way can give you a problem in this. But for purposes of my video, I'm going to go ahead and simplify this completely out. I'm going to distribute, and it doesn't matter whether or not you do the top or the bottom first. I normally start top to bottom just because, I don't know, I always do. Again, it does not matter here. I'm going to go ahead and start with the top because then I can make the line underneath and keep working. It just kind of, it works better from notes. I don't know if it really matters mathematically. Or rather, I know it doesn't matter. I know it does not matter mathematically which one you start with. So let's go ahead and distribute. 3 times 2 is 6. 6, there we go. 3 times 2i is 6i. All over. And now we're going to do this part. Now, I told you earlier that conjugates are going to follow this thing where you eliminate outer and inner. I can't remember if it was in another video or in this video, but the purpose is when you name your conjugate, the reason we use the conjugate is because you eliminate your outer and inner terms. You only have to do your first term and your last term. It creates a difference of perfect squares situation. I'm going to FOIL the whole thing out to prove that it eliminates the outer and inner terms, but I don't recommend that you actually do this. Alright, so let me go ahead and show us what happens when you FOIL. First times first, 2 times 2 is at 4. Outer is 2 times positive 2i gives you a plus. Actually, let me go ahead and highlight in a different color. So 2 plus 2, or 2 times 2i is going to give us 4i. All right, and then negative 2i plus, times 2. Negative 2i times 2, so that's your inner terms, is going to give us a negative 4i. And then our last terms, negative 2i plus 2i, is going to give us that. Let me go back to my original color. So again, negative 2i times positive 2i gives you that negative 4i squared. That was really sloppy, but that's okay. Negative 2i times 2i is a negative 4i squared. What is positive 4i minus 4i? Positive 4i minus 4i is 0. So they actually cancel each other out here. I told you guys the outer and inner terms would cancel out. So our next part of the problem just looks like this. 6 plus 6i, and I'm just rewriting the top all over, and we eliminated the middle part, so let's bring down what's left over. Our 4, and whatever was over here, our negative 4i squared. Negative 4i squared. Alright? We're almost done. We're just going to simplify a little bit further. Remember your I squared. I told you your job is to get rid of this I in the denominator, which we're going to go ahead and do right now. I squared is equal to what? I squared is going to be equal to that negative 1. You guys should be getting used to it. I've said it quite a few times in this video. But 4 minus 4 times negative 1. And then on top was this. Again, I'm just rewriting things for purposes of working it out and teaching. You don't have to do all of this. And then we're going to go ahead and say negative 4 times negative 1 is a positive 4. 4 plus 4 is 8. And then on top you still got this. You are nearly done. This is a pretty good answer, but a lot of teachers are pretty strict about simplifying and reducing your fractions. So let's go ahead and reduce our fraction. You'll notice that 2 goes into all these because they're all even numbers. 2 goes into 8 4 times. 2 goes into 6 3 times. 2 goes into 6 3 times. So our final answer is just, remember our 6, change to a 3. Our 6 again, change to a 3. Don't forget your I. All over 8 turned into a 4. Now you would be done. Your final answer here would be 3 plus 3i over 4 down to the bottom. Alright, so let me go ahead and bring it up on this whole page real quickly. It's kind of a long page, but still. Alright, that's how you would use your conjugate here. Alright, this is as far as I need to go over for this video. There are more complex versions. Obviously, I could have multiple binomials down here. This could be like 2 minus 2i, 3 minus 8i, etc., 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 and it could keep going on. But the point of it all is that you've got your binomial, and you're going to use your conjugate to solve it. Okay? And that's going to cover everything that we need for imaginary numbers for the time being. Anything more complex, you're welcome to call me or ask me or email me or whatever else. Alright guys, best of luck with this. Oh, that's right, I'm sorry. Let me go ahead and bring all the pages up on full screen. That way you can copy them down. Alright, so there's that first page, adding, subtracting, and multiplying complex numbers. Alright, feel free to pause. I'm going to move on to the second page. There's your second page. You cannot have I in the denominator, so with a simple monomial, all we're going to do is multiply by whatever we need to get to the nearest even power. If this were I to the third power, this would also be I over I to get us to I to the fourth. You're mostly always going to multiply by I over I in a monomial problem. That's typically going to be your easiest approach. Okay? Only when you have a monomial in the denominator, and then it gets a little more complex when you have a binomial, and then we're on this page. It's not quite all on. There we go. And so that is that entire page for using conjugates in binomials with I. Alright? So feel free to pause on any of these pages. Hopefully it all helped you out, and I will see you guys in the next video.